Okay, we're just going to finish up some of our notes that we've been taking on the objectives from this unit. And I'm going to just quickly kind of go through what your notes should look like. So over here you have your name. Make sure you have your name there, right? And then yesterday we went through, how three-dimensional solids are connected to two-dimensional figures. So we saw, how you can form these solids, the cylinder, the cone, and the sphere, by rotating rectangles, triangles, and circles. We saw how you can translate, here we have some polygons, triangle, rectangle, octagon. When you translate them, you end up with prisms, right? And that if you translate a circle, you end up with a cylinder. And that if you stack congruent triangles, rectangles, and here's an octagon again. So any polygon that gets stacked turns into a prism, as long as they're congruent polygons. And circles, when they're stacked, turns into a cylinder. And when we stack the similar polygons and circles, and they're similar, progressively smaller, you can create a triangular pyramid. You can create pyramids, and for circles, you can create cones, okay? And then just remember this little bit in here, right, that the solid is named right when we translate or stack, when we translate perpendicular to the base. So that is a right solid, so like a right cylinder, a right prism. And when it's not perpendicular, then we call that oblique, okay? So you know that. We've talked about that a lot of times, but just some reminders. The basic formula for all your prisms and cylinders is to, for the volume of all the prisms and cylinders, is to make sure you find the area of the base first and then multiply it by the height. So B is the area of the base and H is the height, right? To find the area of bases, you got to remember your formulas, right? So the area formula for a circle, pi r squared. For a rectangle, would be, length times width. For triangles, 1/2 times base times height. Or you could do the 1/2 times side times the sine of theta, whenever we know side angle side. For cones and pyramids, you're gonna take the formula, right? So that's the volume equals base, area of the base times the height. And just remember that you're now going to multiply by 1/3 because it is a cone or a pyramid. So you just multiply by 1/3. For spheres, the volume formula is 4/3 pi r cubed. You have to know that. For surface areas, okay, what we practiced in class was unfolding the three-dimensional solid, right? And what we mean by that is sketch it out, right? And then use your area formulas for each of the parts, right? So after you unfold, like, let's say a rectangular prism, you're going to have a little diagram of all the faces, right? And they're going to look like little rectangles everywhere. And you just fill in the dimensions, right? The length, width, height, into each of the rectangles, and then use your formulas for that, okay? And same thing with pyramids, whatever the base is. For a cylinder, don't forget that cylinders unfold and would have a rectangle and two circles, right? For a sphere, there's a special formula, so it's 4 pi r squared for the area, surface area of a sphere. And for the lateral surface area of a cone, you're going to go pi times the radius times the slant height. That's a special formula as well that you need to know and have for your exam. The circumference of a circle is, don't forget, 2 pi r. And that will come into play whenever you're calculating the lateral surface area of a cylinder, because you unfold it, you get a rectangle, but what's that length of the rectangle going to be? Well, it's going to be the circumference of that circle, the circular base that it goes around. So you need to know that, okay? And let's see. We're going to come back to the vocabulary. We've covered vocabulary, and I don't know that we're not going to probably write the definitions in here, but if you're not solid on all of the shapes and these terms, the great circle, the hemisphere, the radius, the diameter, what does right and oblique mean, what are prisms, cones, pyramids, and cylinders, you could put definitions in here, but I don't think you absolutely need to do that. Then you need to be able to find arc length to find the lengths of arcs, or you could use the formula to find central angle measure, or you could use the formula to find the radii of a circle, or for similar circles. So basically, your formula for arc length, which we use the letter S for here, is that it is part of the whole circle. So remember that arc length is part of the whole circle. So part of the oh, look at this. It's not, arc length is not part of the whole area of the circle. It's part of the whole. This is wrong. I see that what we've talked about in there yesterday. So I'm going to fix this here. But the arc, remember, the length of the arc is a part of the circumference. So let me sketch this out real quick and just do like a little reminder deal here. Okay, I'm going to really quickly just, let's see, I don't know, maybe I can make like a circle here, right? So when we talk about the arc length, right, and I'm going to go back to this freehand tool. We're talking about some distance. Let me get another color. Sorry. I'll go with this color here. So we're talking about some distance along the circumference, right? So the arc would be, you know, we're not talking about the sector. We're not talking about the area in here. We're talking about how long is it here. So this right here is S, right? The arc length. So that's important to know because it's part of the whole circumference of the circle. So let me fix that, and let's see, we can close that out and go in here. So it is part of the whole. I'm going to put that word in there, circumference of the circle. So then when we do the circumference formula, we do not want to use pi r squared for that. Okay, we want to use 2 pi r. So 2 times, oh boy, let me get that, sorry. So I gotta insert an equation here, or I want to edit the equation rather. Let me get my equation tool. Let me do this, insert an equation. And that will bring up my equation tools. Okay, sorry about that. I should be able to edit inside of here now. So, okay, so arc length S is, right, equals part. The part is the degrees over 360 of, we're using times, right? And then the circumference formula is 2 times pi times r. So we got to put a pi in here. And then we'll say times the radius, right? And I could just, let's see, copy that and come over here, and it's the same thing. It's the same thing whether we're using radians. The only difference is in the fraction here, was we describe parts. Remember that if we're measuring it in degrees, then we're going to put the degrees over 360. If we're measuring it in radians, we're going to put the radians over 2 pi, right? Because there's 2 pi radians in an entire circle. And here is a quick formula also for radians, right? You can know the angle measure, theta, in radians if you just put the arc length over the radius. So if you have that information, you can quickly get to the measure of the angle in radians. You can find out theta. Okay, now these formulas are good if you need to find arc length. They're also good if you know the arc length, right? So if I know the arc length here and I know the radius, I can plug all of that in. I might just put an x here, right, and solve for x is really what I'm doing. You know, and if I know it in radians, I could put it in here. If I know the angle measure, say in degrees, and I know the arc length, and I need to solve for the radius, well, I plug everything else in. I put in my arc length on this side, I put in my degrees, and then I solve for r, for the radius, right? So that's something you can do. Angular velocity, okay, we have this omega, right, the symbol for omega there, which we use to represent angular velocity. And we say it's equal to the, you know, the angle that was you know, the amount, or I would say the angle that that was passed. So we think about angular velocity. Remember, we think about like the hand on a clock, right? So you have some rotation going on, right? So angular velocity has to do with this rotation. So it's, how many radians around did it go? And remember, it can go more than one time around a circle, right? So it can be a lot more than, say, 360 degrees or 2 pi radians. But basically, you're going to put in the angle, however whatever the angle is, theta, over however much time you have there. And that's our formula for calculating angular velocity. Okay, so our vocabulary terms for sector and segment of a circle, we got to get clear on those just real quick. So a sector, right, is think of a pizza slice, right? The formal definition of this would be the region, we might say, of the circle, or that is, and actually we really ought to say the region of the disk, right? Of the disk. Let me put that in there, right? Because a circle is just the points on the outer edge of the circle. The disk includes all the area inside, all the points inside. So when we're talking about a sector, we're talking about the region of the disk, right? That is bounded by 2 radii and the arc, and an arc, right? So, like I said, it you can think of it looking like a pizza slice, and you need to know that term, right? And we'll get into calculating the area of that sector in a minute. And then for a segment, so the segment is the region of the disk, right, that is bounded by an arc and by a chord. So remember, a chord is a term for a line segment that begins and ends on the circle and goes through the interior of the circle. So maybe I'll just I don't think we need to sketch that out. We've talked about this. This is just a review, but remember that that's what a segment is. And I know sometimes, if it's been a few days, kids might forget what a sector or a segment, or get those two confused. But make sure you know the segment of a circle, right, is the region that's bounded by the arc and a chord. Okay, so how do we find the area of a sector? Well, we're going to do the same thing that we did before, right? We're saying, writing it out in English, this is always a good idea, is to write it out in English, right? So the area of the sector, right, would be equal to a part of the whole area. So this is the part here, right? So many degrees over 360 tells me what part it is. That's the ratio, or the fraction represents the part. Here's of, we use times, and then the whole area is pi r squared, right? And so you'd use this for degrees, and if you're using radians, you're going to do the number of radians over 2 pi, because 2 pi radians in a full circle times pi r squared. So those formulas, we've covered well. And then the area of a circle segment. All right, so here I've written it out, right? The area of a circle segment is equal to the area of the sector minus the area of the triangle. And that triangle is the triangle formed by the radii and the chord. So what you would need to do is you'd put in, theta over 360, or if it's in radians, you could put theta over 2 pi, right? But this is the part of the circle, right? Part of, we're using times, right? And then the area, right? So pi r squared, right? And that will give me, this is the formula right here we're looking at, right? So that would give me the area of the sector, right here, this part, the area of the sector is right here, okay? And then we have to take away the area of the triangle, so we're going to take away the area of the triangle. So the area of the triangle, if you remember that area formula for the triangle, 1/2 times side times the sine of the angle, we can use that whenever we know side angle side. And so in this case, the sides are the radii, right? So it's minus 1/2 times the radii squared times the sine of theta. So this, all I would need to do is I need to know theta, right? I would need to know the radius, and then I could plug it in because we plug it in here, 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 and here's where we would plug that in. And that will give me the area of the circle segment. Now, one thing to keep in mind as you work through these is to make sure that as you're taking sine, that you are checking on your calculator that your calculator is set appropriately for either degrees or radians. In this case, we're talking about degrees, so the sine you're going to take is going to be in degrees, right? Don't get confused about that. Okay, so just make sure you have that set there. Okay, the relationship between the measures of two-dimensional figures and the three-dimensional solids formed through transformation in space. So let's start with a rectangular prism, right? So it has a base, which is the sides of the triangle, right? So the sides of the triangle, and then you have the that is the same as the sides. So that's equal to, let's say, equals the sides of the base, right? And then the height is, the height of the prism. And then for the rectangle, oops, that is a rectangle, sorry. Rectangular prism, we would do the sides of the rectangle. Sorry about that. Is equal to the sides of the base. And then the, if we're doing a triangular prism, same thing. The sides of the triangle equals the sides of the base. Okay. And this would be, for translations, pretty straightforward, right? For a cylinder, the radius of the circle is equal to the radius of the base, right? And could also be for a sphere, we would say the radius of the disk that we are rotating is equal to the radius of the sphere. Now, these are all created when we are creating these by translation, right? Well, this one's by rotation, but these are by translations. Let me put that note in here. So by translation, we would use those dimensions. Pretty straightforward there. But by rotation, it gets a little bit different, right? So we rotate a circle, then we get the radius of the sphere. And when we rotate other objects, we have to pay for other objects, right? Pay close attention to the axis of rotation. So what are we rotating around? So let me give you an example of this real quick. Okay, if I were to say have a rectangle, I think I have a box here. So okay, if I had a rectangle, right, and let's say that this measured, like, I don't know, 4, and this measured 1, right? So we have a rectangle that is 4 across by 1. Well, it all depends on where I'm going to rotate it. So I'm going to show you two different rotations, or two different axes of rotations here. The first one we'll do is if I were rotating it along this axis, right? If I were rotating it along that axis right there, well, then this would end up being the radius, right, as it spins around. Let me try to get a little dotted line here, right? So basically, if I'm rotating, I am like going around in a circle, right, like this, and coming back around. That's not very good, but you get the idea. Well, then 1 would be my radius, right, if I rotated it this way. If I put the axis right in the center, then it would be half of this, because 1 would be the full diameter. But what if I rotated the other side over here? So I'm gonna get a line here. So what if I were to rotate along, this axis right here? Well, then what would happen is that I would have, a circle. As this rotates around it, we would end up with a cylinder, right? So this would be the radius 4, right? Both of them are going to create a cylinder by rotation. but now the radius is 4, right? Because it's going to swing all the way around that axis right here, this axis of rotation. And this would be the height. So it just kind of depends on where you're rotating it around. So on the test, I know they're going to say something like, rotate this around the x-axis or rotate this around the y-axis. So just be clear what you're rotating around and then look at the dimensions and think, if I'm rotating around, is one of the edges a axis of rotation? If so, then the other edge will be the radius, right? And and that's how that will work. Okay, so just kind of keep that in mind. And then I guess we can do a triangle here real quick. Let's try to do a triangle here. Oops, let's go with a triangle. So I'll make one that appears to be isosceles, right? So now, again, I've got to look at my axis of rotation. So if my axis of rotation is down the center, I know that's not well drawn there. But if it is, and let's say that, there's my, if this measured, let's say, 4 units across, well then, as I rotate this around, I'm going to rotate it in, go back here and change that color to blue. It is blue, okay? And now as I rotate this around, right, the circle is, these points are going to go right around and they're going to end up back over here and vice versa. So we're going to end up with a cone and the radius is going to be, half of this side of the triangle, length of this triangle, right? And that's when the axis is directly here. If I have a right triangle, and then the height would be the same as the altitude. The height of the cone would be the same as the altitude of the triangle. If I had a right triangle, so let's see if I can make a right triangle here real quick. Do my best to, right, so. And let's say I were rotating that right triangle along an axis here, right? So then what we would end up with is we would end up with this swinging around, and you'd have a cone. Then this dimension would be the radius, and this dimension would be the height of the cone, okay? So there isn't an easy way for me to write that. You just have to know that, and you have to understand that. And the key is to pay close attention to the axis of the rotation, and then you would know, okay, this measure is equal to that. I would see how I'm sketching them out here. I would, if you had an image, I would take your pencil on the test and literally just draw, a copy of where you're rotating around, so that you can get an image of the base, right? In a rotation, you're almost always getting some form of a circle, whether it's a cylinder, or it's a sphere, or it's a cone. You're going to get some kind of a circle. And then that'll help you figure out what the radius is, right? So I think that's all I'm going to put there for you. And we worked on those before, but just want to make sure. All right, so comparing and converting between radians, degrees and radians, you could use a solve command in a calculator, right? The idea is that the ratio that for you to keep in mind, there are 360 degrees and 2 pi radians. So this is the conversion ratio, right? So I would know that my radians have to be equal to my radians over the degrees. So if let's say I wanted to solve for my radians, I'd put x here, right, theta or something, and then my degrees I'd put down here. So if it's a 90 degree, I would put 90 down here and x up here, and then I could solve, and either using a solve command or multiplying by the degrees to get it over there. And then if I'm going the other direction, right, I could still fill in my radians on top here and put the degrees down here on the bottom, and then there's a little more algebra involved, which we won't get into, but again, you can always use a solve command. You just make sure that you are solving. If I want to find degrees, I put the radians in, use this ratio, these equivalent ratios, and then just solve for the degrees. But the key is just to remember there are 2 pi radians for every 360 degrees, so you could just use that. And then the last thing here, it says, use the Pythagorean theorem in problems involving areas of sectors of circles. So let's just take a look at what that might look like on a test, okay? So first of all, we're going to have to start with a circle. So let's get an approximate circle here. Okay, and then if it is a area of a sector, well, you have to remember to use Pythagorean Theorem, and Pythagorean Theorem deals with right triangles. So this is only helpful, perhaps, when you're dealing with the area of a sector, to figure out perhaps the radius, although you could just use what we've seen before, but we just want to make sure you're comfortable with the Pythagorean Theorem as well, and we'll type that out. Ooh, boy. Let me undo that. Let's see if I don't know if I can do this. Nah, I don't know. Let me just hit erase and start again. Okay, so here's my circle, right? And then something like that. And then to use Pythagorean Theorem, what I would be doing is I would be having a right. This will only work for sectors, right, that are 90 degrees, right? But now I know these radii are equal to each other, and so I could use Pythagorean Theorem. So I'd have to have a right triangle here. So if I needed to solve this length of this chord, I could use Pythagorean Theorem. So let's remember, what is Pythagorean Theorem? Well, it is leg squared plus the leg squared equals the hypotenuse squared. And again, that only works for right triangles, so you'd have to know that this is a right angle for sure, 90 degrees. And then you could put in the formula leg squared plus leg squared equals hypotenuse squared, and that would help you, to perhaps, you could use that to help you calculate the area of the segment. So how would that happen? Well, first I would be able to calculate the area of the sector. The area of the sector is going to be, if this is 90 degrees, it's 1/4 of the circle, right? It's 1/4 of the circle. So find the area of the circle and take 1/4 of it. That'll give me the whole area of the sector. But then I could use Pythagorean Theorem here. And let's say I knew this was 10. Well, what we're probably going to do is, if I know this is 10, and then I know these are radii, they're equal to each other. So then what I would do is I would say this is x here, and this is also x. And so now I can use that to calculate. See, I don't know the, if I don't know the radius, but I know the length of the chord, and I know that this is a 90-degree angle, then I can use the length of the chord and solve for, these here. So let me type something out here just real quick. Be a little clearer what I'm saying. Let me put some text over here, and I'm going to just, I think I will just go with a white background and go with maybe a dark blue or something like that. Colored text, I don't know. So what I would be saying here is I'd be saying, okay, if I knew the area or the length of the chord, and I knew that the angle, that theta, let's say that theta was 90 degrees, right? Then I could use Pythagorean Theorem to solve for the radius, right? Which we would need to know the radius. So how would I do that? I would say the radius equals x, right? And so then I could put it in my calculator to say x squared, right? Plus x squared equals the chord squared, right? So the hypotenuse squared, and I would solve it for x, where h is equal to the chord or the hypotenuse, right, which is a chord, whatever the chord length is. So this is where this would come in. I have to look at the test again to be sure we're, be clear on what we're testing here. But essentially, there's likely to be a problem here where they're going to say, okay, solve for the area of the segment or the area of the sector, and the only thing we know is that we know the chord measures a certain length and that the angle theta is 90 degrees. And then that would allow us to say, okay, we don't know the radius, so how can we find the area? Well, we can solve for the radius. If we know the chord is this and we know this is 90 degrees, then x squared plus x squared equals the hypotenuse or the chord length squared, right? Solve for x and you know the radius, and then you can use the formula given above. Okay? So that's enough there, I think. You should be able to, let's see if I can, oh, we lost it. Anyway, you should be able to, oh no, maybe I can move this. No, I don't think I can. I don't know. Well, I don't. Anyway, if you need to pause that, write that down or whatever. Write something down in your notes similar to that. You should be good. And that's everything you need to know to be able to take this test, okay, and do well on it. Do your best. Take your time. Don't race through it, okay, because it's important, right? We want you to do well on it. And I will be with you after spring break. Thanks and have a great day.